Good evening, guys. Hope you're doing well. We're going to get into free energy equilibrium now. Hopefully, this won't be as bad as it's been like the last couple of times I've tried it. And then hopefully, we'll be able to move forward and get the rest of these up in the next couple hours so that you guys will have them. I apologize for how long this has taken, and I'm going to hurt somebody if this doesn't go better. So let's go ahead and share so that you guys can take a look at what we're talking about here. And let's see if we can get a slideshow started on this. So again, we're talking free energy and equilibrium. And this is going to take us through the end of chapter 18 that we're going to be talking about. So we'll talk about the standard electrode potentials, which will tie back to what we've been talking about with redox. We'll do the effective concentration on cell EMF, and then we'll start talking about thermodynamics, and that'll move us into our further discussions of thermodynamics for other topics as we move forward. Okay? So hopefully you don't have any questions. If you do have questions, comments, problems, concerns, please let me know. I will be more than happy to do what I can to help. And let's see. All right, so let's see what we can talk about here. So this is a slide that we've talked about in the past. This is from our voltaic cells lecture. I want to show you how the information that we had from that ties into where we're going right now. And we tied the balancing the redox reactions and that the reduction being at the cathode, the oxidation being at the anode, the oxidation LEO on the left, so lose electrons, oxidize on the left, reduction on the right, and the reduction occurs at the cathode, red cat. So we can walk through Zn, going to Zn2 plus 2 electrons. We lose those electrons. That's our oxidation that occurs at our anode. Those electrons go up through our zinc solid into this wire and then through this voltmeter. Through the voltmeter, they come out and come down into our cathode, which is our Cu solid that's being formed. And we have Cu2 plus being reduced with 2 electrons to Cu in this cell over here. So what we're measuring, okay, at this voltmeter is actually our EMF. So it's the cell potential, the energy that is different between the oxidation half and the reduction half. Now, let's go ahead and talk through some of the terms that are related to this. So we're going to go ahead and look at our next slide. So electrons flow spontaneously one way in a redox reaction, from high to low potential energy. The potential difference between the anode and the cathode in a cell is called the electromotive force, the EMF. It's also called the cell potential. It's designated as E cell. Okay. Now we can find these tabulated. They're always listed as reduction half reactions. Okay, so it's always gain electrons reduced in those tables. All right. Those values are independent of the stoichiometry of the reaction. So even though we have to multiply these reactions in order to get the right number of electrons being transferred sometimes, that does not change the value of the cell potential. Okay, the only way that we can measure these cell potentials is against something else. So it's not an absolute value. It's something that we measure in a difference type way. And so in order to do that, we have a couple of things that we need to look at. One is, what is the standard against which we measure that? And I'll talk about that in just a second. And two, we know that there's only that potential difference that we're looking at. Now, that potential difference is measured in volts. 1 volt is 1 joule per coulomb. Okay. Reduction potentials from many electrodes have been measured and tabulated. They're measured against the standard hydrogen electrode, which is 2H plus, aqueous, 1 molar, plus 2 electrons going to H2, gas, 1 atmosphere. Now, we have specifications for this, what phases they're in and what the concentrations are. So that 1 molar for the aqueous component, the 1 atmosphere for the gas. Those are standard conditions, and that's listed as our standard hydrogen electrode, the She. Everything is measured against that. Okay, so that's our standard for this. Now, these standard electrode potentials, the one that you're looking at here on the left is the one that you'll find in the exam handouts. The one that you're looking at here on the right, I have actually pulled off of the internet because it has some other values in it that I wanted to be able to use. So if it's not on the values that you were given in the handouts, you'll have to be given those values. And excuse me, that may occur. All right, so these are all written as reductions. We see that there's a value for the E naught in volts, so that assumes that these are standard potentials. So gases are at 1 atmosphere, any aqueous components are at 1 molar. Okay, so those are the things that we're looking at for these. Now, let's see how we can use these standard potentials. So we're going to be coming back and looking at this table. These values will either come from this table, or I've pulled them off the internet somewhere. So all the values that you'll see today are from somewhere. If they're not in this table that you get on the test, it'll be something that I've pulled from somewhere, and therefore you would have to be given that as well. Okay? Now for standard conditions, we can use the following to calculate the E for the cell. So the E standard for the cell equals the E standard reduction for the cathode minus the E standard reduction for the anode. Okay? Where E cell is greater than 0 for a spontaneous reaction. So if it's going to be spontaneous, we have to make sure that it's occurring in the direction that will give us a greater than 0 potential. All right. For these two half reactions, where we're talking about Zn solid going to Zn2 plus 2 electrons, and Cu2 plus 2 electrons going to Cu, the voltage that we measure for that is 1.10 volts. Okay. That comes from the anode in this cell, the E naught reduction for that being negative 0.76 volts. And that's for our anode over here for the zinc. And for the cathode, the E naught reduction is 0.34 volts. So that's for our copper over here. Okay. To get our overall E for this, we again have the E naught reduction for the cathode minus the E naught reduction for the anode. So the cathode, 0.34 volts, minus the negative 0.76 volts gives us that 1.10 volts, okay? And again, we're looking at electrons traveling up the zinc into the voltmeter when we measure this, then down into the copper to do that reduction at the copper, okay? Yes. Thinking through something in my head. Now we're going to look at a couple of other ones about this in just a second. But one of the other things I wanted to talk about is this is how your textbook presents this, is that it's an E naught reduction cathode minus E naught reduction anode. There is another way to think about this, and this is the way that most people I find tend to look at this. What we look at is that since we know that one of these is the reduction, okay, so gain electrons reduced, this reduction occurs at the cathode. So the Cu2 plus 2 electrons goes to Cu. This is the reduction. So we would leave that voltage exactly as it exists. But the other one occurs as an oxidation. So since we've reversed that reaction when it happens, we reverse the sign of the E. So rather than looking at this as the negative 0.76 volts, we'd be looking at this as a positive 0.76 volts. And if we reverse that, then we just add those two values together. So what you'll see down here at the bottom is the E naught cell equals the E naught reduction cathode plus the E naught oxidation for the anode. So where you flip that sign. This is an easier convention to remember, and so it's the one that I prefer. But since your textbook presents it differently, I'm going to present it in both ways for a lot of the things that I do. Now, we want to look at a couple of other reactions here. I want you to calculate the E naught cell for oxygen converting to hydrogen peroxide reacting with Mg, Sn2 plus and Zn, and Li plus and F minus. Okay. So what I'm going to do is I'm going to show you my little piece of paper that I have. And this is my paperwork that I've put up for you guys to be able to look at. So one of the things that we're considering is oxygen converting into hydrogen peroxide. So O2 plus 2H plus 2E minus goes to H2O2. The potential for that is 0.68 volts. And that's from here. And of course, we can zoom in a little bit. O2 plus 2H plus 2E minus goes to H2O2 is 0.0 0.68 volts, and that's what I've written right here. The other one we want to talk about is the Mg reacting to give me Mg2 plus 2 electrons. Now, that's not how I'm going to find it in the table. Okay, this is written as an oxidation and not a reduction. So when I find it in the table, it's going to be Mg2 plus. So let's see if we can find that Mg2 plus, and that should be down here a little bit. And it's actually not in that particular table. It's in this one. Mg2 plus 2 electrons goes to Mg, and that's listed as negative 2.37 volts. Okay. Now, notice when I wrote it the first time, I wrote it as an oxidation. So I wrote the reverse reaction, Mg solid going to Mg2 plus 2 electrons. And I wrote it as a positive 2.37 volts. The second time I wrote this, I had O2 plus 2H plus 2E minus going to H2O2, which is 0.68 volts, just like it was before. But now we're looking at Mg2 plus 2 electrons going to Mg solid. And that one is written as negative 2.37 volts. So just as it appears here as a reduction. Okay. When I do the E naught self in this second case, it's going to be the E naught reduction for the cathode, so the 0.68, minus the E naught reduction for the anode. So I'm going to subtract the negative 2.37, which then gives me 0.68 plus 3.05, or plus the 2.37, which gives me 3.05. When I did this up here, I had the 0.68. I had reversed the Mg reaction and that gave me a plus 2.37, and that gives me 3.05. So no matter which way I do it, I should end up with the same value. Okay, it's just your preference as to which way you do that calculation. Okay, I again have shown you both the way your textbook does it and the way that I do it when I reverse it and put it as a reduction. Okay. So now I'm going to go back. Let me zoom to fit. Apparently it's not going to let me do that. See, I shouldn't have zoomed. I hate it when I do that. So. Fit the window. That's what I. Okay. And then we were back here. So that was our oxygen converting to hydrogen peroxide reacting with Mg. We then talk about SN2 plus Zn. So SN2 plus 2 electrons goes to Sn. I found that in my standard reduction table as 0.13 volts. And then I have Zn2 plus 2 electrons going to Zn, and that reduction potential is negative 0.76 volts. This is written exactly as it would appear on those reduction potentials, so both of them are reductions. I've boxed the two species that I want, so SN2 plus and Zn, because that's what it said we wanted to look at the reaction for. So I know that SN2 plus occurs the direction that it's written. The Zn is actually the reverse, so I'm going to reverse this voltage, and then I have my E naught reduction plus the E naught oxidation equals 0.13 volts plus 0.76 volts, which gives me 0.89 volts. The other way I can do this is the E naught cell equals the E naught reduction for the cathode, so the tin, minus the E naught reduction at the anode, so minus the negative 0.76, which again gives me the 0.89 volts. Okay, so that's what we're looking at there. The other one I want you to consider is Li plus F minus. So Li plus an electron goes to Li. That's negative 3.04 volts. F2 plus 2 electrons goes to 2F minus. That's 2.87 volts. And remember, I boxed the Li plus and the F minus. So I'm going to have this negative 3.04. And when I reverse this, that's going to be a negative 2.87, right? So I'm going to end up with a negative 5.91 volts. If I do this as the E naught cell equals the E naught reduction cathode, that leaves me with a negative 3.04 volts minus the E naught reduction anode, which is the minus 2.87 volts, which again gives me negative 5.91 volts, okay? So I've calculated the standard cell potentials for those reactions as they were requested. Now, are we always going to do that? Maybe, maybe not. But let's take a look at where we're going next and let's see what we can figure out. Now, the more positive the value of E naught reduction, the greater the tendency for reduction under standard conditions. So if it's way up here, this F2 plus 2 electrons going to 2F minus, it's very positive, very likely that F2 is going to turn into 2F minus. Okay, it's very easy for F to pick up electrons to make that happen. So it's very favorable for it to do the reaction as it's written. Okay, and that's because it's so positive. Now, the strongest oxidizers have the most positive reduction potentials. So if they have the most positive reduction potential, therefore they are likely to be reduced themselves, they are causing oxidation in something else. So the higher the value is, the more positive it is, the more likely it is to be able to oxidize something else. The strongest reducers have the most negative reduction potential. So if they want to be oxidized, they're going to have a negative reduction potential. A reducing agent causes reduction in something else. An oxidizing agent causes oxidation in something else. So a material on the left of a half reaction will react with any material below it on the right, because if it's on the left, it can be reduced, and the material below it on the right can be oxidized, and that's a favorable process. Okay? Now, a couple of things that you may or may not have noticed from that. If it's up here, right, that's a very positive value. So we're looking for spontaneity with it being positive. So we're going to talk about that a little bit more, but that's what we're going to be talking about. Now we're going to use our standard reduction potentials to look at these particular reactions. We want to look at what is the overall reaction that we're looking at. What's the anode half reaction? What's the cathode half reaction? The cell notation and the overall cell potential. Okay. Now, I've asked you to look at fluorine gas and lithium, lead and manganese, oxygen and acid and mercury, silver and nitrate. Okay. So my paper says overall reaction, cell notation, E naught cell, anode half reaction, cathode half reaction. I've asked for fluorine gas and lithium. From the standard reduction potential table on slide 5, I took F2 plus 2E minus goes to 2F minus with an E naught of 2.87 volts. I have lithium solid going to Li plus an electron. That's E naught equals negative 3.0 volts. Okay. Now, my F2 is gaining electrons. So gain electrons reduced. Reduction occurs at the cathode. So this is my cathode half reaction, and it's positive, 2.87. My LiS going to Li plus an electron. This lose electrons oxidize. So this is my anode. My E naught for that particular reaction is negative 3.04 as it's written in the table. Okay. F2 is the reduction because that E0 is greater, E naught is greater than 0. Li plus is the oxidation, the reverse reaction, because E naught as a reduction potential is negative. So if we use the E cell equals the E naught reduction for the cathode minus the E naught reduction for the anode, we get an E0, an E cell, which is greater than 0, which is 2.87 minus the negative 3.04 equals 5.91 volts, which is greater than 0 and spontaneous, as written. Okay. Let's talk about the next one. So the next one I ask you about, it says lead and manganese. Oh, and my overall reaction, because I did ask you for that, is F2 plus 2 Li plus goes to 2F minus plus 2 Li solid. And I wanted the cell notation for that. So if my reactant is F2 gas, and that becomes F minus as the reaction that happens over here on the left, that's going to be F2 gas with a phase change to F minus aqueous. So that single line is a phase change. In order for that to happen, I have to have an inert electrode present because neither of those is solid. So that inert electrode is the PT, and that's solid, which is what the S is for. Those three occur as one of these two cells. We then have the double line, which indicates a different cell. In that cell, I have two Li plus going to Li. Now, I don't need to show that there are two of them, not in this case, because the reaction that happens is Li plus going to Li. I have two of them that are required to balance this out, but I don't need to show that in the cell notation. Okay. Now, since I'm going from an aqueous to a solid, there is a phase boundary between those two, but the solid is a solid by itself, so it doesn't need an inert electrode. So this is my full cell notation for that. Okay. The next one I ask you to consider is lead and manganese. So lead and manganese, lead is Pb2 plus 2 electrons goes to Pb solid. Mn2 plus 2 electrons goes to Mn. Okay, so I said lead and manganese. All right, I look at both of these and I see that this is a negative 1.3 volts. This Mn, as it's written, is negative 1.18 volts. I know that if I want this to be a spontaneous reaction, I'm going to need it to be my E to be greater than 0. So I'm going to reverse the Mn. I'm going to go from Mn solid to Mn2 plus 2 electrons. That means that my E naught cell equals the E naught for reduction for the cathode. So since I'm going to reverse this one, this is going to mean I lose electrons oxidized at the anode. This is going to be my gain electrons reduced at the cathode. So my Pb is the cathode. Okay, so that means I'm going to have the negative 0.13 at the cathode, and I'm going to subtract the negative 1.18 volts that occurs at the anode to give me 1.05 volts total. That cell potential is greater than 0, so that's spontaneous as written. Writing that for the way that we're doing this, it's Pb2 plus Mn goes to Pb solid plus Mn2 plus. Now I've got a solid on the Mn and a solid on the Pb, so it's Mn solid, phase boundary to Mn2 plus aqueous. Then I have another cell with Pb2 plus aqueous going to Pb solid. And that's my full cell notation, my overall reaction, my full cell potential, my anode half reaction, and my cathode half reaction. Okay? So now let's look at oxygen in acid and mercury. So oxygen, O2 gas plus 2H plus 2E minus goes to H2O2. That's a positive 0.68 volts as written in the table. Hg2 plus Ag plus 2E minus goes to 2Hg liquid is plus 0.85 volts. So since this is the bigger positive, this is going to stay a reduction. So it's going to be Hg2 plus 2 electrons goes to 2Hg liquid. But the H2O2 is going to get reversed. And so it's going to be H2O2 going to O2 gas plus 2H plus aqueous plus 2E minus, which is going to be the negative of this. Now, when I calculate my cell this way, it's E naught cell equals E naught reduction for the cathode, the 0.85 volts, minus the E naught reduction for the anode, so minus the 0.68 volts. So if I change the sign and add them together, it's 0.85 plus plus a negative 0.68, which gives me a positive 0.17 volts for the overall. Positive cell potential is spontaneous as written. We get our Hg2 plus H2O2 going to 2Hg liquid plus 2H plus O2 gas. Now, I have my H2O2, which is aqueous, going to 2H plus aqueous and O2 gas. So I need a platinum electrode, something solid, to make this work. So I have a platinum solid electrode, phase boundary to H2O2 aqueous, phase boundary to O2 gas. Okay, that's what happens in one of these cells. The other half, the other cell, is going to be my H2 plus aqueous going to 2Hg liquid. That's not a solid, so I need my platinum solid electrode to make this work again. I have to have a solid present to make this work. So I have platinum on both sides of these, and I have H2O2 going to O2 and Hg22 plus going to Hg liquid. Okay? Questions, comments, problems about that? Awesome possum. The last one I asked you about is silver and nitrate. So I have silver and NO3 minus. I find NO3 minus aqueous plus 4H plus 3E minus goes to NO gas plus 2H2O liquid. That's plus 0.96 volts. I have Ag plus E minus goes to Ag solid as plus 0.8 volts. Since the NO3 is more positive, that's the one that stays as a reduction, we reverse the Ag plus. So it's Ag solid going to Ag plus E minus. My E naught cell is going to be the E naught for the reduction, which is at my cathode. So this guy right here, my 0.96, and I subtract the E naught reduction for the anode. I subtract the 0.80. That leaves me with 0.16 volts overall for the E naught cell. I have NO3 minus plus 4H plus Ag solid going to, and it's 3 Ag solid because I need 3 electrons. Goes to 3 Ag plus NO plus 2 H2O. That's my overall reaction. Okay. Since I have Ag solid going to Ag plus, there's a phase boundary between the solid and the aqueous. But this is Ag solid, so that's going to stay the way that it is. We then connect that to another cell. I have NO3 minus aqueous going to NO gas. Neither one of those is a solid, so I need that platinum electrode in there to make this work. So that's my overall cell notation for this. Questions, comments, problems about what I did or why I did it. Anytime you do not have a solid for one of the species that you're looking at in a particular half reaction, you need a solid inert electrode. We almost always use platinum just because it is really inert. It doesn't react with a lot of things. And so it's always something that you can use. Now, are there other things you can use? Absolutely there are. But we want to make sure that we're consistent in picking something. So just like we often use NaNO3 in our salt bridge because Na doesn't react with anything, NO3 minus doesn't react with anything, then that gives us a good basis for making a salt bridge. We're going to use platinum as our inert electrode because it won't react with anything. Okay? Questions, comments, problems on any of that? So, a couple of takeaways. You want to build this as a positive E cell. Okay, whatever you have to do to make that work, that's the way it's going to go. All right, so your reduction is going to be the more positive reduction potential. Your oxidation is going to be the less positive reduction potential, or negative. That's how you're going to determine which one goes which direction. Okay, we want to have our lose electrons oxidize anode on the left, our reduction red cat on the right. Okay, those are going to be how our two half cells are built. We want to make sure that we are losing electrons at our anode, gaining electrons at our cathode, and that we then travel that direction, and that we have a cell potential that matches that. Okay. Even though we had to multiply some of these to get them the balanced equation, so NO3 minus plus 3 Ag plus, we did not change that E naught for that cell. Okay, it didn't matter. We only had to write it differently when we wrote the balanced equation. Now, if I never asked you what the overall equation was, you wouldn't have to worry about that. Okay, so that's where that comes into play. Questions, comments, problems. If you have them, I think you know how to do it. So, a couple of implications of the E naught cell. All right. So electrons flow spontaneously one way in a redox reaction from high to low potential energy. So spontaneous means a reaction that does occur under a given set of conditions is spontaneous. If it doesn't occur that way without intervention, it's non-spontaneous. We'll talk about that in a little bit. All right, that's where we're going to be going after this topic. So how do I know if a redox reaction is spontaneous? The E cell, the value of that will tell me if it's spontaneous. E naught cell is under standard conditions, 1 molar solutions, 1 atmosphere pressure. It's what we calculate from the standard reduction potential tables. Okay, so that's important. My E naught cell can be, so E cell can be under any conditions, doesn't have to be standard. If E cell is greater than 0, it's a spontaneous reaction. That is called a galvanic cell. So a galvanic cell is spontaneous. If the E naught cell is less than 0, that's a non-spontaneous reaction. That's an electrolytic cell. And that's because we have to use electricity to drive it. So that's why it's an electrolytic cell. Now, voltaic cells can be either. It doesn't matter if it's spontaneous or non-spontaneous. Voltaic cell just means we have a cell that's based on a redox reaction. Okay. If the reaction is non-spontaneous, it doesn't occur on its own. It can be driven to occur, but we have to put in energy to make that happen. Okay, so that's what we're talking about with that. Questions, comments, problems on any of that? Hopefully not, but if you have them, please let me know. You know how to contact me. So let me know if there's anything you have concerns about. So the next thing we're going to talk about are non-standard conditions. We've talked about standard. We know that we can calculate that based on what's in the standard reduction potential tables, but it's not always standard conditions. And as a reaction continues to proceed, we're going to be losing material. So we're going to go from a standard condition, so 1 molar. If we leave it long enough, it's no longer going to be 1 mole. And therefore, we're going to have to look at what is that. So the way that we talk about non-standard conditions, we have a relationship that's given by this reaction here, okay? Non-standard could be any part of the reaction, so we could just change the concentration in the reduction. We could change it in the oxidation. We could change it in both of them. We could change it for the gas, but not the aqueous, or the aqueous, not the gas. It could be any combination of those things. There are no guarantees. That's what we're going to see under non-standard conditions. We need a way to look at all of the conditions that may exist. So all of those species, since they can be part of this, need to be looked at. How do we look at things that are not what we typically see? We talked about this a long time ago. Remember that quantity Q? Q was under non-equilibrium conditions, right? So since non-equilibrium is something that has a potential, it's going to be something that can go forward, we can use that to look at these particular conditions. So what's going to happen is that our E for the cell is going to be equal to the standard potential minus 0.0592 over N, where N is the number of electrons that are transferred, times the log of Q. Okay, where Q is products over reactants raised to their stoichiometric coefficients, just like we've talked about before. Okay, nothing has changed there. Hopefully that's something you remember. Now, this equation right here is called the Nernst equation. All right, it has two forms. I have E equal to E naught minus RT over NF ln of Q, or E equals E naught negative minus 0.0592 over N log of Q. And that's when we make a couple of assumptions. So we're assuming that we're at 25 degrees C, and so we can get rid of that temperature component. We then multiply it by R and divide it by F, and that's where we get all the happy numbers except for the N. And then we're looking at a natural log, a base 10 log rather than a natural log. So that's where what's different between those two equations. So let's take a look at what this looks like in practice. So consider the following cell diagram. I have magnesium solid going to magnesium sulfate at 0.4 molar, connected to NiSO4, 0.6 molar, going to NiS. So our two aqueous components are non-standard. And we want to calculate the cell voltage for this at 25 degrees C. So our E cell is equal to our E naught cell minus 0.0592 over N log of Q. N, in this particular process, we go from Mg to Mg2+. So that's a 2-electron process, okay? And as Ni2 to Ni is a 2-electron process. So N equals 2. Q is going to be products over reactants. So MgSO4 is a product in this. So we go from solid to aqueous component. from aqueous component to solid component. So our product is the Mg, which is 0.4 molar. And our reactant is the Ni2 plus, which is 0.6 mole. Okay, so product 0.4 over reactant 0.6. And again, they're both 1. So that's our Q. Now, our E naught cell for this is 2.120 volts, and that's calculated from the standard reduction potentials. So our E cell equals 2.125 volts, and it says see handouts for scratch work. Well, all right, what handouts am I talking about? I'm talking about these guys. Let me make that actually show up. Okay. So Mg2 plus 2 electrons goes to Mg solid. That's negative 2.37 volts. Ni2 plus 2 electrons goes to NiS is negative 0.25 volts. Now, as this is written, we know that it's not going from Mg2 plus to Mg. It's going from Mg solid to Mg2 plus. So this is the one that's my oxidation. It's this negative 2.37. So Mg solid plus Ni2 plus goes to Ni solid plus Mg2 plus. So that's how I know what's in my reactants and products, okay? But I can also tell it from the cell diagram as it's written. Because again, this is my reactant and my product, my reactant and my product, okay? So my E naught cell equals the E naught reduction for the cathode, all right? My cathode is my gain electrons reduced at the cathode. So that's this one, the negative 0.25 volts. I subtract the E naught reduction for the anode, which is, I'm subtracting the negative 2.37 volts, which gives me 2.120 volts. So that's my standard. I then set up my E naught cell equals 2.120 volts minus 0.0592 over 2 times the log of 0.4 over 0.6. And when I do all that happy math, it gives me 2.125 volts. Now, I've only left this as 3 decimal places so that you can see how little variation we have in doing this, okay? When I reduce my, it says, how does the voltage change when Mg2 plus is decreased by a factor of 4? Mg2 plus goes from 0.4 over 4 to 0.1. Then my E naught cell goes to 2.143. Okay, and that's this math right here. This math is for when we've reduced our Ni2 plus from 0.6 to 0.2, which is the one we talk about right here. How does the voltage change when Ni2 plus is decreased by a factor of 3? So that's that 0.2, and that gives me 2.111 volts. And if Ni plus changes after the Mg2 plus changes, so we have both changes. So we have the 0.1 over 0.2, that gives me 2.129 volts, okay? Decreasing the product makes the reaction more favorable. So we have a higher E cell if I decrease the product, okay? If I decrease the reactant, it makes it less favorable. So I have a lower E cell. So less reactant means I can't go as far forward. So that I see a lower E for that, all right? One of the other ways that we can see non-standard conditions is when we create something called a concentration cell. When I make a concentration cell, I have the exact same reaction in both halves. So the reactant and, the reduction and the oxidation are the same reaction, but they're different concentrations, okay? So we're going to look at Ag electrode in 0.15 molar AgNO3 and an Ag electrode in 1.0 molar AgNO3. Okay, so we have Ag plus an electron going to Ag solid. That's an N equals 1, and it's 0.0 or 0.80 volts for that. Now my E for the cell is going to be the E naught for the cell minus 0.0592 over 1 log of Q. Now, my E naught for the cell is really interesting here because I have Ag solid going to Ag 0.15 molar, and that's connected to an Ag at 1 molar going to the Ag solid. So my Ag plus is higher than my Ag plus over here. So this side is higher than this side. This side needs to come down. This side needs to go up. We're trying to equalize those two concentrations. And so we want to drive the 0.1 up and drive the 1.0 down. So the reaction proceeds as written. So Ag solid going to Ag plus in the 0.15 side, and Ag plus going to Ag solid in the 1 side, okay? My E naught for the anode minus the E naught for the cathode equals 0 because they're the same value. So 1 is positive, 1 is negative, that means 0. So my E naught for the cell equals 0 minus 0.0592 over 1 times the log of Q. My product is the 0.15 molar. My reactant is the 1 molar. So that gives me this log of 0.15 over 1, and that gives me 0.0488 volts. Now, as time goes on, and that 0.15 comes up and that 1.0 comes down, there's going to be less driving force to move that forward. And so this voltage will go down. That is what we see based on Le Chatelier's principle. Okay, so all of this ties back together into what we've already talked about. Okay, questions, comments, problems on that? Let's give you some practice for concentration cells. So the value of E naught cell with the following reaction is 1.10 volts. What is the value of E cell when the concentration of Cu2 plus is 1 molar and the concentration of Zn2 plus is 0.025 molar? And we're looking at Zn solid plus Cu2 plus going to Cu solid plus Zn2 plus. Now this is the one that we talked about a little while ago. This is the voltaic cell that we had initially that we were looking at, where the overall cell was 1.10 volts. Okay, so since my concentration of Cu is 1 and my Zn is 0.025, that means that my product is 0.025 over 1. My reactant, which is 1, that gives me this expression right here. It's a 2-electron process. So that leaves me with, instead of the 1.10 volts, under this set of conditions, we're looking at 1.14 volts. Okay? So that's the concentration effect that we have from that. All right? One more. And actually there is some calculation with that. Now this concentration cell, I did not write anything on my piece of paper because I did all of this work in Excel. Here I have 4H plus Fe solid going plus 3NO3 minus going to Fe3 plus NO plus 2H2 liquid. So the Fe I don't care about, the solid, and the H2O liquid I don't care about. But I have a concentration for H plus, I have a concentration of NO3 minus, I have a concentration of Fe3 plus, and I have a concentration of NO aqueous. So I can set all of that into my Q, right? And I have my standard for this, which is 0.189 volts. So I have my 0.189 volts minus my 0.0592 over 3, since it's a 3-electron process. And then I multiply that times the log of 1.0 times 0.5. Both of those are, their stoichiometry is 1. Divided by 0.10 to the 4th times 0.60 to the 3rd. And that's all of that happy math. So 0.1 to the 4th, 0.6 to the 3rd equals 0.189 minus the 0.0592 over 3 times the log of 23.23148.15, which then gives me my 0.01029 volts. Okay, so we've gone from 0.189 to 0.1029. Right? So concentration is an effect there as well. This is what the stoichiometry looks like when we have factors in front of those values. We have to remember that when we set up our Q, we have to take those stoichiometric coefficients into account. So that's another concentration cell that you can look at there. Does anybody have any questions, comments, problems for that? I hope not, but if you do, please let me know. All right, a couple more. Let's start talking about thermodynamics. So when we talk about thermodynamics of redox reactions, actually, let me make this bigger. thermodynamics is something that we talk about in detail in the next couple of lectures. It's something that has to do with the spontaneity of a reaction. So again, if a reaction is spontaneous, it occurs without any action being required. If that's true, the value of delta G, the free energy of the reaction, is negative. Now, we'll come back to this in a couple of lectures, and I'll show you how all of that pans out. But for now, I need you to understand that that's the case. For now, understand that E cell can tell us if a reaction is spontaneous as written. If the reaction is non-spontaneous, it requires an input of energy to proceed. If that's true, the value of delta G is negative. No, is positive. Oh my God. Oops. It's negative if it's spontaneous. It's positive if it's non-spontaneous. In the case of voltaic cells, we can tell if a reaction is spontaneous by looking at the value of E cell or E naught cell. If E cell is greater than 0, it's spontaneous. If it's less than 0, it's not spontaneous. As we'll describe later, the delta G for this is equal to minus NF E naught cell, and delta G equals minus NF E cell. Okay, so what this means is that we can directly calculate the spontaneity, the free energy that's associated with this from the E of the cell. Okay, and like I said, we will come back to this in detail in a few slides. All right, so now we see that E cell is related to free energy. We need to show that E cell is also related to the equilibrium constant K. So E cell equals 0.0592 volts divided by N times the log of K. Oh my God, that looks almost exactly like what we had when we had that log of Q under non-standard conditions, right? So what that means is if we know the value of EMF for this cell, we can calculate the equilibrium constant, which tells us if we favor products or reactants, and how much do we favor them. So if we know E naught cell, we can calculate K. If E naught cell is greater than 0, that is a spontaneous reaction. Okay, we just talked about that. So E is positive, that's spontaneous. Delta G is negative. K is greater than 1, which means that product formation is favored. So written as it's written, we want to go forward. All right, so if delta G is negative, K is greater than 1, E naught cell is positive, and we favor formation of the products as it's written. If delta G is 0, K is equal to 1, the E naught cell is 0, we are at equilibrium and neither reactant nor product is favored. If delta G is positive, K is less than 1, and E naught cell is negative, we favor the formation of the reactants. We're going to go backwards. Okay, so this is all tied together with everything that we've talked about before. So the K doesn't go away, it has come back. Le Chatelier doesn't go away, it has come back. All of these things are things that we need to be able to tie together, right? And that's what we're going to be doing in the next few lectures. Now, if I know delta G, or if I know delta E, or if I know K, I can calculate the other values. Now, this happy little triangle is not going to be provided to you on the test, but you will get all of these reactions, okay? So these relationships will be there. So you can still get E naught cell 2K through delta G. When you're practicing, be aware that that's not on the test, and you will provide practice for this once we cover delta G. So once we get to the exam through practice, and then hopefully the practice for each of these lectures, you will see how these things are related. And I want you to do that practice with your handouts for the test. Okay? So that's that. That's how all of that stuff, the thermodynamics, is connected. All right? Questions, comments, problems on anything that we've talked about for this? Again, I hope not. But if there are, please let me know. I will make this available as soon as I can. It's going to take me a little while to get it uploaded to YouTube so that you guys can see it, but I will get this to you as soon as I can. Thank you guys. I appreciate it. I will talk to you soon. Thanks.